Let me put up my hand. No, that's the wrong button. Let's go to this screen over here. All right, let's take a look at what we have going on this week. First hour right here, Algebra 3. Yeah, this is moving along quickly. It's moving along quickly. We go to our grade screen. See, last week we had 2.01, 2.02, so you should have that turned in already. This week we're covering 3 lessons: building functions from functions, inverse functions, and then graphing transformations. We're throwing a lot into this week because next week we have the practice test and the test. So we're only going to spend just a couple of weeks here going through module 2. So what that means is after we take the test, module 1 will be closed basically. Anything you have missing from module 1 needs to be in by the time that we test module 2. That's how my late work policy works. It's in our syllabus that, you can turn in late work until we're done with the next module. So you got basically like 2 weeks. If you haven't turned in some of the stuff from module 1, you've got 2 more weeks until it's done forever. So that's where we're looking. I just want to remind you guys of that. So let's look at our 3 lessons: building functions, inverse functions, and graphing transformations. If we go over to activities here. All right, so we're on building functions from functions. There's not a whole lot in the notes here at the beginning of the lesson, but there's a lot in it. See, the overview only lasts, you'll see, here's the scenic overlook. That's what we look at. It goes to, come on, load up. It's slow loading. Oh, see, this is lesson right here. So it's only a page and a half. The scenic overlook, the summary is a page and a half, which is what we usually cover. But there's a lot in this page and a half. So we're going to do some examples and look at it a little more in detail. But it talks about building functions from functions. 2 functions can be combined by either adding them, subtracting them, multiplying them, or dividing them. Right? So if we have f of x divided by g of x, right? This is a whole, f of x could be x squared minus 3x plus 4. I mean, f of x is an entire function, and it's being divided by another function. So in this case, why must we restrict g of x to be non-zero? We say if we divide f of x by g of x cannot equal 0. Well, that's for the simple reason that you cannot divide by 0. In mathematics, that's an error. That's a problem. You can't do it. It doesn't work. So if g of x is 0, that's dividing f of x by 0. So in that case, we have to restrict it. So let's define this. Let f and g be 2 functions with overlapping domains, which means they're not exclusive. They both have some of the same x's, at least one of the same x's. Then for all x common to both domains, right? For all the x's where they both exist, the sum, difference, product, and quotient are defined as followed. So if we have f plus g of x, that's the same as taking the 2 functions and adding them together. So I'm going to write that in my paper as the first example. We're going to look at f plus g of x. Okay. I'm going to sharpen the pencil here. The difference works a lot the same way. F minus g of x is the same as taking f of x and subtracting g of x. Product, multiplying them together, fg of x, that just means taking f of x and multiplying it by g of x. And then that dividing thing, f divided by g of x, is f of x divided by g of x, but g of x cannot be 0. All right. And then the compositions is where f of x and g of x would be f of g of x. Now, I know you did some of this in Algebra 2, but we're looking at it again as a good review here. And this is actually taken from some pre-calculus class. So after you learn it in Algebra 2, we use it a lot going forward. So if you have f of g of x, that's the same as taking g of x and substituting it into f of x. So the domain of that is the set of all x in the domain of g, such that g of x is in the domain of f. So everywhere has in common. So it says the best way to learn this concept, working through examples in the online textbook. So here's the online textbook. So let's look at how some of these examples work. So I'm going to put up, let's see, I'm going to move this over where I can see it on another screen. And then we're going to put up this screen. All right, f plus g of x. So f plus g of x just means we take f of x and add g of x to it. So let's take a look at that in actual example here. So let me pull up an example from our online textbook. So let's say that f of x is going to equal x squared. Okay, that's the entire f of x function. And g of x is going to equal the square root of x minus 1. Okay, that's our two functions. And we're going to start out first with f plus g of x, which means we just take these two, f plus g of x is going to equal f of x plus g of x. That's it. And the domain would be x is greater than or, oh, it's just greater than it. No, it's greater than or equal to 1. Oh, this is x plus 1. Let's make this x plus 1. So we can do this negative 1. Might be easier to deal with the x plus 1. I put the wrong equation. X is greater than or equal to negative 1, and it's only restricted because we cannot have a negative value under the square root. We can't take the square root of negative 1, square root of negative. That's imaginary. It's not a real solution. So we have to restrict the domain of this. In this one, there's no restriction to the domain. In this, that's the domain of this and this. Because this has a restricted domain to start with. It cannot be a negative number. This has no restrictions. But when we combine them, we have to take the most restrictive one. The all real number domain is now canceled out because it has to be greater than or equal to negative 1. All right, let's look at f minus g of x. All right, that's the other example. So this f plus g of x means you add them together. This means we subtract them. So we simply take the first one and we subtract the second one. And again, we have the same domain. I'm going to just put ditto marks. Ditto marks. Same the restrictions of the domain. Now, I want you to be careful with this because had this been, let's look at one different thing. What if g of x would be x plus 1? If this would be g of x, then this would be x squared minus x plus 1, which when you simplified it, would be x squared minus x minus 1. So if there's more than one term, we're subtracting all of those terms. Minus x minus 1. But in this case, it's all underneath the square root. So it's just one term. So we just subtract it. But be careful of this case here where there's two terms. You gotta distribute that negative 1. You have a negative out front, that's like a negative 1. So we have to distribute that. So let's go back to here. All right, now how about fg of x? Fg is when you multiply together, right? So we're going to take x squared times square root of x plus 1. And it has the same domain restrictions. X has to be greater than or equal to negative 1. That's as simplified as it can get. We can't simplify that any further. So that's just what it ends up. If we do f divided by g of x, then that's x squared divided by the square root of x plus 1. And this has a further restriction. It changes just a little bit. the domain. Up here, it was okay if it was equal to -1. Because -1 plus 1 is 0. The square root of 0 is 0. We're okay with that. Here, we can't have 0. So the domain is x is greater than -1, not equal. We can't be equal to anymore. And we can also write that -1 to infinity, if you like writing domain that way. This would be bracket -1 to infinity, because it includes the -1. Here it does not include the -1, because we cannot have a 0 in the bottom. So this is how we combine functions. Functions inside of functions, function operations, multiplying two functions together, adding them, subtracting them, whatever we need to do. But we just simply add them together. Add this one plus that one. And simplify if possible. Let's look at it as a different example. If we have f of x equals x squared plus 2x, and g of x equals, let's just say it's x minus 5. Different case here. X squared plus 2x, x minus 5. So now if we do f plus g of x, that means we take x squared plus 2x, and we add to it x minus 5. We're adding that to it. This is not a final answer because this could be simplified. We got 2x and 1x, so that means it's x squared plus 3x minus 5. That's what it equals when you add them together. If we have f minus g, x squared plus 2x minus x minus 5, 2x minus x, x squared plus x minus -5 plus 5. We write it out this way, so that way we don't forget anything. Got to distribute the -1 to both terms. So 2x minus x is just 1x. Fg of x, where we multiply them together, that would be x squared plus 2x times x minus 5. We got to distribute x squared times x is x to the third. X squared minus 5 is minus 5x squared. 2x times x, 2x squared, and 2x minus times minus 5 is minus 10x. So we simplify that. These we can combine because they're both x squared. So it equals x to the third minus 5x squared. Oh, I'm sorry, minus 3x squared because we added 2 to it. Minus 5 plus 2, negative 3x squared. And then we have the minus 10x in the end. So this is what it equals when we multiply them together. And then dividing them, f over g of x is x squared plus 2x divided by x minus 5. We can't really simplify that. This is the same thing as x times x plus 2 over x minus 5, but still that doesn't simple. If this had been x plus 2 in the bottom, see, then we could factor it and cancel those out and we'd end up with just x, but it's not. It's an x minus 5. So this is fine as the simplified. That's what it equals when you do f divided by g of x. Okay, so that's what this lesson is about. Being able to just take functions and put them in functions. So there's the example with the x squared and the square root of x plus 1. There's other ones down here. F of g. We didn't do f of g. We need to do that. F of g. And let's see if there's any other. F of g, F, G. Okay. All right, most of the rest of it is f of g of x. So let's look at that then. All right. In this second example, using these same two equations, so we've got this and this. We'll probably do f of g more often than these others, so pay attention to this. F of g. It looks like fog or something there, but it's not. It's like a little circle. What that means is you take f and substitute g of x inside of it. Actually, I don't even need that first parentheses. It's the same as f of g of x, which means you take, if we had f of x, we substitute in for x, whatever number we want. Well, in this case, it's saying substitute g of x in for x. So that means we're going to take, instead of x squared, we're going to take x minus 5 squared. Because what are we substituting in for x? G of x. What's g of x? It's x minus 5. So x minus 5 goes in place of the x plus 2 times x minus 5. See, we substitute x minus 5 everywhere there's an x, because that's what this said to do. Instead of f of x, it's f of g of x. So g of x is substituted in everywhere there's an x in the equation. X squared plus 2x. Now we have to simplify this. So we got to take x minus 5 times x minus 5. So I'm going to write that differently just so I can not mess up the math if I write it out. Plus, I can go ahead and do this math, 2x minus 10. So what's x minus 5 times x minus 5? Well, we got to distribute, right? Got to distribute to the first and second, distribute to the first and second. X times x is x squared. X times negative 5 is negative 5x. Negative 5 times x, negative 5x. Negative 5 times negative 5 plus 25 plus 2x minus 10. So this simplify, distributed. And then we still have the 2x minus 10 at the end. So now let's just combine like terms. It's x squared, negative 5x, negative 5x, and that's negative 10x plus 2x over here. So we have negative 8x. We have plus 25 and minus 10, 15. So that is f of g of x. Taking g of x, substituting in f, it equals this equation. So that's the combination of both of those, substituting them one into the other. We can go the other direction. Let's look at the other direction on that. We can say g of f of x, which is the same as g of f of x. That's it. You may see it written either way, g of f of x or g of f of x. This time we take f of x and we substitute it into the g equation. So we have, instead of x, we've got x squared plus 2x minus 5. See, instead of x, we just substituted f of x in for that. And then it's already basically simplified. So it's x squared plus 2x minus 5. That's what it equals. Notice that is not the same as the other way around. F of g of x is x squared minus 8x plus 15, but g of f of x is x squared plus 2x minus 5. Most of the time, they'll be different. They could end up the same, but only in special circumstances. So get good at this. G of f, f of g of x, g of f of x. Practice that. That's the only way to get good at it, is practice that. Substitute one equation into the other equation and then simplify. And then simplify. All right. Because we're going to need to know how to do that in our next lesson here. Let's look at the next lesson. Inverse functions. All right, you may remember inverse functions from Algebra 2. You may not. All right, So let's see. A function's shown as a set of ordered pairs. Let's talk about that. A function of x can be written as f of x equals 2x. But what does that look like if we have points? So if we've got 1, 2, 3, 4 as the domain is the x's, right? 1, 2, 3, 4. And the range would be 2, 4, 6, 8 because the function is f of x equals 2x. So 2 times the x. You have 1, 2 times the 1 is 2. You have 2, 2 times the 2 is 4, and so forth. So that means f of x equals 2x contains these points. The 0.12, the 0.24, the 0.36, the 0.48. Those are all points on the function 2x. If we reverse those, that's the inverse function. So I'm going to write these points down. If f of x has the points 1, 2, and 2, 4, and 3, 6, 4, 8. Okay. This is good to catch this too. If this is points that are on f of x, it's the point 1, 2, 2, 4, 3, 6, 4, 8. If we have the inverse, if you remember from function notation, that's how we say the inverse. This is the inverse of f of x. It's going to contain these points. 2, 1, 4, 2, 6, 3, 8, 4. It's the exact same points, but they're reversed. The x is now the y is now the x. So if f of x contains these points, the inverse would contain these points. Inverse. Okay. Oops. Went the wrong way. There we go. So it's notated with the little f of -1. So I was just showing you there. F of -1, that's the inverse. All right. Oh, and here's a little link. Will it actually take me to that link? It may or may not. No, that link doesn't work. Sorry. It's just talk about what that is, f of -1. So how would we find the function, the inverse function for that? All right, so there are steps to finding the inverse. So this is good to have in your notes, unless you remember this really well from Algebra 2. Finding the inverse. So if we have this function, let's look at the same function we've been looking at here, f of x equals 2x. So number 1, rewrite as y equals. Rewrite. That's not a very good rewrite, but that's all I'm getting today. So we're going to make it y equals 2x because remember, this is the same thing, f of x or y of x, or y, f of x or y, same thing. So that's the first thing we do is rewrite it. Second step, swap x and the y. So we'd say x equals 2y. We just swap them. Everywhere there's an x becomes a y. Everywhere there was a y becomes an x. All right. Then 3, solve for y. Solve for y. How do I get y by itself? Divide by 2, divide by 2. So y equals x divided by 2. So we can write that as the inverse. Right as f of, there we go, right? 4 steps. Write it as the inverse. So that means the inverse of that function, x divided by 2. So these are inverses of each other. If f of x equals 2x, f inverse of x equals x divided by 2. Now let's look at something interesting there on Desmos. Let me go to Desmos. We're going to put these two functions in and see the graphs of it. f of x equals 2x. That was our first function. Right. I change this again where it just shows by ones. I don't want all these little halves. Oh, step 1. There we go. All right. And remember, we said it had the points 1, 2, 2, 4, 3, 6, and 4, 8. Label those 4 points. And we said if we find the inverse, it will have the exact opposite points, 2, 1, 4, 2, 6, 3, and 8, 4. We said the inverse should have these 4 points. Well, let's see. We found the inverse, so let's graph it. We'll graph it as y equals x divided by 2. Well, there's the inverse, and it has those points. There's the 2, 1, the 4, 2, the 6, 3, and the 8, 4. All of those are on the inverse. So what we see with Desmos is exactly what it said we would see. It said if these points exist on f of x, we can reverse those points, and they will all be found on the inverse of f of x. And that's exactly what we saw. Because we algebraically found the inverse using these 4 steps. And the inverse did have those points. So it's important to know how to find the inverse for this unit. All right, let's go back to this. The notation is 2 functions are inverses if for the functions f and g, f of g of x equals x, and g of f of x equals x for every value. Wow. Okay, so this is how you prove that a function and the inverse are inverses of each other. And I believe this is on the quiz, is on the test. You'll see this, so you need to know how to prove this. You prove this by finding f of, I'm going to say f inverse. F of f inverse in this case. So that means we substitute what f inverse is in for x. So in this case, it would be 2 instead of x divided by 2. Well, what is 2 times x divided by 2? Well, if we multiply by 2 and divide by 2, those cancel out. That just equals x. How about the other way around? What if we take the inverse and substitute f of x into it? We're going to take the inverse equation. Instead of x, we're going to substitute this into it. 2 of x divided by 2. Oh, well, 2 divided by 2 is just 1. That equals x. If you substitute the inverse equation in for x and it equals x, and you substitute f of x into the inverse and it equals x, that proves that these are inverses. Usually what you'll see is they will say, okay, this is f of x, and let's say it is x plus 2 divided by 3, and this is g of x, and it is, let's see, 3x minus 2. Are those inverses of each other? And they'll say, prove that they are or are not inverses of each other. And you're like, okay, well, let's see. How would I do that? Well, you do it just like this. We substitute g of x and f of x and see if it equals x. And then we substitute f of x into g of x and see if that equals x. So let's try that. Let's see if these are actually inverses, because I just made these up. Trying to see if it worked. So f of g of x See it? That's the exact same equation, f of x, but instead of x, we've substituted g of x in for the x. So let's simplify this. 3x minus 2 plus 2. Minus 2 plus 2, that's 0. So we have 3x on top, and the bottom we have 3. Well, what's 3x divided by 3? Just x. It's 1x. Okay, so far so good. We're halfway there. That worked. Does it work the other way around? G of f of x. If I take f of x right here and substitute it in for g, substitute in for x on the g, 3 times, I'm going to make it big because I got to put a fraction in here, x plus 2 divided by 3 minus 2. See, that's the g of x equation, 3x minus 2, 3x minus 2, but instead of x, I've substituted f of x in for it. So let's simplify that. What is 3 times x plus 2 divided by 3? Well, those canceled out. So that's just x plus 2. That's just x plus 2, and then minus 2. So x plus 2 minus 2. Oh, yes, these are inverses. Yes. These two equations are inverses of each other. Let me show you something on graphing that as well, because there's something else I want you to know about. I'm going to put that in parentheses so it's all over 3. Put x plus 2 divided by 3. If I don't put that in parentheses, it won't put everything on top of the 3. And g of x, we said, was 3x minus 2. All right, let's check what we know to be true. Oh, look, 1, 1 is on both of them. Let's see. Here's a point that's on this equation, 2, 4. Not going to keep it up there for me. So that means 4, 2 should also be there, right? So if we go over here, there's 4, 2. Looks like 7, 3 is there. So we should find 3, 7 on the other one. Where's that? There it is. It's right there, 3, 7. Here's the secret to graphing functions. This is a reflection over the line y equals x. Y equals x. And that's why if 7, 3 is a point, if the y equals the x and the x equals the y, then that means 3, 7 is also on the inverse. Because it's a reflection of the line where the y equals the x equals the y, equals each other. It's always a reflection. When we look at those other two equations that we graphed earlier, we had f of x equals 2x, and then we had, let's say g of x, but the inverse of it was x divided by 2. Look, it's a mirror over the green line of y equals x. Inverses are always a mirror over y equals x. All right, but the important thing is knowing how to prove it, that they will equal x, when you do f of g of x. That's why I said it's important to learn that from the first lesson, how to substitute g of x into f of x and simplify. Here's one for you to practice. It wants you to determine the inverse function. So use this, go through those 4 steps. You didn't put those in your notes. Rewrite it as y equals, swap the x and the y, solve it for y. You can rewrite it back as the inverse function. These are the steps. Need those in your notes so you can do that. So you need to find the inverse function there and then prove it. And it calls it the identity function. That's where you take f of g of x and g of f of x and prove that they both equal x. And then you can check your answer there. So here's the graph and the inverse, our mirror images. We just talked about that. Over y equals x, the y equals x line. So if xy is a point, then yx is the line. So here's another one. X to the third minus 3. find the inverse of that, and then graph them both and show that it's a reflection of y equals x. Again, you can check your answer right here. All right. Not all functions have an inverse function. Just to let you know right up the bat. Not every function has one. By definition, an inverse function exists only if no two elements in the domain point to the same element, right? Because if more than one element in the domain, if more than one x point to the same y, if you did the inverse of that, it would no longer be a function. So we're not having an inverse function. So an example of a function without an inverse is y equals x squared. Now let's look at that real quick and see, why does that not have an inverse function? Y equals x squared. Let's do that y equals x line. Okay, y equals x. It says this does not have an inverse function, because the inverse of that would be x equal y squared. And that's not a function. It fails the vertical line test. When x is 3, the y is 1.7 something there. I can't get right on the 3. Anyway, when x is 1, is the y 1 or negative 1? Because it exists in both places. It's not a function. The green one here is not a function. Yes, it reflects over the y equals x, but it's not a function. So it's not an inverse, because the inverse is an inverse function. See, an inverse function. It's not a function. So not all functions have an inverse function. All right. Let's see. For most functions, we can follow a process to determine the inverse, replace the fx with the y, replace every x with y and y with x, and then solve for y. That was those steps I was talking about. Rewrite it as y equals, swap the x with the y. So everywhere there's an x, make it a y. Everywhere there's a y, make it an x. And then solve for y. All right, then you can rewrite it as f of negative 1x is the inverse function. So here's the actual lesson. If you need to go through more examples, this will talk more about it. It talks about here that's not a function because it fails the vertical line test. So you can give a horizontal line test to a function to see if it has an inverse. This one does not have an inverse. So the horizontal line test, just to see if a function exists. One-to-one. A function is one-to-one. And what that means is every x only has one y, and every y only has one x. See, we've talked about a function where every x only has one y. This is talking about an extra thing, one-to-one. One-to-one means also that every y only has one x. So it's important to know what the definition of a one-to-one function is. Every x only has one y, every y only has one x. All right. The inverse reflection, that's a reflection of y equals x. We covered that too. F of g of x, g of f of x would equal x. If it's a one-to-one function, if it's a one-to-one, it does have an inverse, and they would both equal x when we substitute in there. So, all right, let's look at our last lesson. It's a little different. It's graphing transformations. Graphing transformations. You've done a lot of transformations in other math classes up to this point. You've done it in Algebra 2, Algebra 1, and even in geometry, you've probably looked at some of the transformations. But we're just talking about how it works for all kinds of functions. So in algebra, we talk about a constant function. We talk about identity function. We talk about absolute value function, the square root function, square function, and cube function. So here's a picture of all 6 of those. If you're not familiar what those functions are, let's take a look at what their graph looks like. So the graph of a constant function, when it loads, it's being very slow loading today. Here it goes. Come on. There it is. Constant function. That's just where like it equals a number. F of x equals 2 or y equals 2. In this case, it looks like y equals 1.5. That's just a horizontal line. The identity function is that y equals x. It's that horizontal diagonal line. I'm not horizontal. That diagonal line that inverses reflect over. That's the identity function. The square function, square function, that's square root. I'm sorry, that's x squared. I mean, that's the parabola. The cubic function, cubing function, on another line underneath there because you can't have the square root of a negative number. That's why it doesn't exist over here in the x's, and that's why there's no y's down there, because if we take the square root of something, we'll never get a negative number, so it doesn't reflect down here, and it doesn't exist where x equals negative numbers either. And then absolute value, that looks like a v, absolute value function. So that is the 6 primary functions that we use in algebra. So let's talk about horizontal and vertical shifts. All right. So let's just use the graph we have here. If we want this to go up and down, transformations, and this should be kind of a reminder for you because I know you've covered this in other algebra classes. All we have to do is put something on the end. If I want it to go up 5, plus 5. It goes after the equation, after the x squared. That works on the same thing in like a, let's say y equals x. If I want that to go up 5, I just put plus 5. And look, now it's up here. Instead of it 0, 0, it's 0, 5. If I want it to go down 3, minus 3, I put a minus 3 on the bottom. If I did the same thing up here, instead of plus 5, made that minus 2, it would just go down 2. So vertical shifts are just added to the end of the equation, whatever kind of equation it is. How about a left and right shift? What if I just want this to move over here to where the x is at 3? I have to put that inside with the x, parentheses x. Would I say plus 3? You think so, but that makes it go left. That makes it go left because you'd have to go plus 3 to get back where it started. Left and right is the opposite sign of what you think it is. Up and down is the same sign. Plus 5 makes it go up 5. But plus 3 makes it go left 3 into the negatives. If I want it to go right, I have to subtract 3. So x minus 3 squared. Even this other equation, if I want this, I can put this in parentheses and say x minus 3. Now it's moved to the right 3. It was going through 0, 3. Now it goes through 3, 0, negative 3. Now it goes to 3, negative 3. We take that away. Let's do it like that. Goes to the origin, but if I wanted to move it over here to where it's 3, I just put a minus 3. Now it's over here at 3, 0. So left, right is the opposite of what you would think. Okay. So if you want to shift up or down, we change it to a plus C, where C is whatever number you choose. That would make it go up or down. To go left or right, negative 5 would shift it 5 units to the right. It goes the opposite direction. All right. So what effect does the constant have on each of these graphs? If we have x squared minus 6, that's going to make the graph go down 6. How about plus 3? X plus 3. That's going to make the graph go up 3. But how about in parentheses with the x? Now we changed the x. We haven't changed the end. We've changed the x. Instead of x squared, it's x minus 6. This is going to make it shift 6 units to the right, to the positive values. To the right. And if we do plus 3, that's going to shift it left. All right, let's talk about a reflection shift. A reflection shift is different still. Let's go back to our x squared. There's x squared. That means you put a negative out front. If I put a negative out front, it reflects it downward. Now, I'm not going to say it reflects it over the x-axis because that's not necessarily true. It just reflects it downward. Well, another glitch here, but I'm just illustrating the difference between reflecting downward and reflecting over the x-axis. If I put a negative out front of that, does it reflect? If it reflects over the x-axis, it's going to be down here. But if it just reflects it downward, oh, see, it did not reflect over the x-axis. It reflected downward from exactly the same vertex it was at. It was at 0, 5. The vertex is still 0, 5, but it's reflecting downward. See? Just downward, not over the x-axis, downward. There's another case in here. Let me do this first so we can see this. X plus 2. All right, now I've gone up 5 and I've shifted it left 2, right, by putting the plus 2. If I put the negative out front, again, it's going to reflect it downward. But what if I put the negative with the x inside the parentheses? That's going to reflect it over the y-axis. Over the y-axis. That actually went over the y-axis because it was on the left side by 2 spaces. Now it's on the right side by 2 spaces. So outside reflects downward. Inside with the x, if I put it with the x, it's going to reflect it over the y-axis. Kind of different there. So the reflection of the function f of x equals x squared is negative x squared. And that's going to be a mirror reflecting it downward. All right, non-rigid transformations. There's one other one that we need to do as our summary. Non-rigid. Now that means these are rigid transformations, which means that parabola is the exact same parabola it was even before we made it go up 5. It's still the same shape. Even before we made it go right 2 or left 2 or however we move it, it's the same parabola. But if I put a number in front of the x, 5, now I have a different parabola because I'm multiplying it by 5, so it goes up 5 times faster. See, it has the point 1, 5. Oop, where's that? 1, 5. If I take away the 5, it goes through 1, 1 because it took the y value and multiplied it times 5 and moved up to 1, 5. When I put it, if I put a 3 out front, we expect this 1, 1. Here, let's put these points on there. 1, 1. There we go. And the point 1, 3. We expect if we put a 3 out front, it's going to move it up to the point 1, 3 because the y is going to get 3 times faster. Just put the 3 in there. Yep. See, now it goes through 1, 3. We just multiplied whatever x squared was, times 3. And we'll see that. If we go the other way, how about if we go 0.3? Let's make that a 0.3. So I expect it'll go through the point 1, 0.3. 0.3. There it is. Now it got wider. It is wider. It's compressed vertically. We push this point down. We compress that point down to 0.3. All right. So that's a non-rigid transformation. That changes the shape, causes the shape of the graph to change. This is certainly not the same as the original. The original is y equals x squared. It's a very different parabola. It's a much wider parabola. It's been compressed downward. So that is the graphing transformations. Let's look at the lesson that goes with this one. I mean, the assignment that goes with this one. I expect there may be a few graphs on it. No graphs. You have to actually visualize it or put it on Desmos. Describe how the graph of y equals x squared can be transformed to this graph. Y equals x squared minus 20. How can we take x squared and make it minus 20? Do we move it left 20, up 20, down 20, or right 20? That's what I was doing. So when it puts a minus 20 on the end, what happens? How about when we put a plus 17 inside the parentheses with the x? Inside with the x. Left, down, up, right. How about when we put a 9 plus 9 inside and a minus 3 on the end? Left the graph of square root of x to the square root of negative x. You may need to use Desmos to figure that out. But the negative is in with the x. And then this one, is this a horizontal or vertical stretch? So does this stretch it out horizontally or does it stretch it up and down vertically? Right? Just think about that. This is stretching it horizontally here from the blue to the red. We've taken it and we made it wider. We stretched it this direction. If we did this, this would stretch it up. The green one is stretching it upward, stretching it vertically. So that's the type of questions you're going to have on the graphing transformations. On the other ones, you're going to have questions about inverses and f of g and all that good stuff. Let's look at the 2.03 assignment. That was the first lesson we looked at. Find f plus g of x. Here's f of x. There's g of x. What would it be if you add them together? 4 choices. How about f plus g of x with these two? 4x plus 7, 3x squared. How about multiplying them? F times g of x. All right, you may need pencil and paper. I'd recommend it. F times g, multiplying those. How about dividing f by g in this case? Along with which restriction would you need to the domain? What can x not be if we're dividing? There's a number that x cannot be because we cannot divide by 0. Find f divided by g again. Now here's f of g of x. So we've basically got 2 problems of each kind, basically, right? F of g of x. When you substitute g of x in for the x and simplify, which one of those equations will you get when you simplify it? And there's another one, f of g of x. When you substitute g into the f and simplify, what do you get? 8 questions. 8 questions. And finally, let's look at 2.04. Find the inverse. Do those steps. Change it to y equals, swap the x and y, solve for y, and then write it back as an f of inverse. What is that? Or is it not 1-to-1? That's an option where it doesn't have a function because it failed the vertical line test. There's more than one x for each y. Find the inverse of this function, x to the third minus 3. Find the inverse of this one, 6x third minus 8. Determine, is this 1-to-1? Is there only one x for each y and there's only one y for each x? Yes or no? 50% shot. And then here's the one you actually have to work. Prove that f of g of x equals x and g of f of x equals x. So you have to substitute one into the other, and this time do the exact same equation. So you're just doing the same thing twice. Substitute g of x into f of x and simplify it. Show me the steps to simplify that, and the other way around. So one problem you got to write out. That's not bad. For 3 lessons, you only have one that you actually have to write out for 3 different assignments. All right. Told you we was throwing a lot at you today, guys. And next week, we will have our practice test and finish up functions. I'm not going to spend much time doing this f of g stuff. So get your practice in, look at the lesson, do what you need to do. And that's it. We're through today. Let's call it a day, guys. This is an A Friday. So this class will meet again on Wednesday and Friday. If your grade's below 70%, you will need to attend. All right. Have a great day, guys. Bye-bye.